I'm going to be talking about joint work with Nathaniel Johnston and Aravindan Vijayaraghavan. Today I'm going to be discussing the following basic question. So you're given a classical description of a basis for a linear subspace of CD tensor CD, some bipartite Hilbert space, and you want to determine if that subspace contains any product vectors. And if it doesn't contain any product vectors, we say it's entangled. Okay, in other words, if its only intersection with the set of product vectors is just the zero vector, we say that this subspace is entangled. This has a few different applications. First, the range criterion. So if you're given a density operator, rho, on CD tensor CD, and you look at its image, this is a linear subspace of CD tensor CD. And if that subspace is entangled, if it has no product tensors in it, product vectors in it, it turns out that rho is also entangled. So this gives you a sufficient condition for verifying that a mixed state is entangled. Entangled subspaces can also be used to construct entanglement witnesses and quantum error correcting codes. So today I'll be describing a classical algorithm for solving this problem. It'll just be a one-sided algorithm, so it can just certify that a subspace is entangled. But we'll extend this to a complete hierarchy, which really solves this full decision problem. I'll show you an extension to other notions, certifying other notions of entanglement in a subspace, and then present a robust generalization, which I'll use to extend the symmetric extensions hierarchy of DPS for certifying separability, determining separability of a mixed state to determining other notions of separability. So first, this basic problem of determining if a subspace is entangled or not is NP hard in the worst case. The best known algorithm takes exponential time in the square root of the local dimension. It turns out that using some algebraic geometric techniques, you can say a lot just based on the dimension of the subspace. So if the dimension of the subspace is too large, then it actually must contain a product vector. So, you know, for example, if U is the entire space CD tensor CD, then of course it contains product vectors. And it turns out that even if the dimension of U is a little less than D squared, it still must contain a product vector. So the relevant regime is when the dimension of U is less than this number. That's when the problem becomes non-trivial. It turns out that if U is generically chosen and has dimension less than this number, then it must be entangled. It's kind of intuitively, entanglement is a generic property. So what this means is if you pick U at random according to the Haar measure of this dimension, then with probability 1, it's going to be entangled. So what we've kind of encountered is like kind of a hay in the haystack problem, or analogous sort of a similar sort of problem where we know that a generic subspace of the right dimension satisfies this property that we want, being entangled, but we want to show that a particular instance, we want to have an algorithm that shows that a particular instance satisfies this property. So the first thing I'll show you today is an algorithm, a polynomial time algorithm that either outputs fail or it outputs a polynomial time certificate that U is entangled. And this algorithm actually works extremely well. So for the purpose of this talk, I'm going to call this a work extremely well theorem for this algorithm. This is what it says is that if U is generically chosen and its dimension is at most a quarter of the maximum possible, where the regime we care about, then our algorithm will actually output a certificate that U is entangled. So it's like a polynomial time certificate. So you kind of lose a little bit in the dimension, but if you up to this, if you have this limited dimension, you now have a polynomial time certificate for entanglement. I want to mention there's also a third component to our algorithm, which I won't get into today, which is that it can actually output a separable state in U if one exists. And we can obtain a similar type of theorem for this part of the algorithm, which says that if U contains a generic planted separable state, then the algorithm will actually output that state. But I'm going to focus on the certification part of the algorithm today. So here's the algorithm. The idea is that this problem is difficult because it's nonlinear. This set of product vectors is not a linear subspace of CD tensor CD. It's kind of difficult to work with. So you can do something very basic, which is just to make it linear by looking at the span of the set of product vectors and intersecting that with your set U. Of course, this doesn't work because the span of the set of product vectors is the entire space. So instead, you lift it up, or we lift it up. So, and we look at, instead of looking at 2 copies of CD, we think about go up and make the problem a little larger to 4 copies of CD, and consider this sort of lifted space of product vectors. So you take the span of the set of product vectors, tensor themselves 2 times. So if you do this and you kind of rearrange the subsystems, you're looking at a space basically like psi, tensor phi, tensor phi. The psi tensor psi span the symmetric space of 2 copies of CD. The phi tensor phi span the symmetric space of 2 copies of CD. So this is where you get this equality here. And what you do is just check if U tensor twice has any intersection with this set I'm calling X sep 2. It turns out that this is non-trivial now. I mean, this is X sep 2 is no longer the entire Hilbert space, so there could be something non-trivial going on, and it turns out that this actually works very well, this very simple algorithm. So here's this algorithm again, a little more concrete. So you just check if these spaces intersect. If not, you output that U is entangled, and otherwise you output fail. And this algorithm is correct in that if U contained a separable state, then the algorithm will always output fail. Because if, say, psi tensor phi is in U, then psi tensor phi tensor twice, of course that's in U tensor twice, and it's also in X sep 2. This is a one-sided algorithm for this problem. So not only does this algorithm work extremely well on paper, we have this theorem, it also works very well in practice because it's just a linear system of equations. So for example, for 10 local Hilbert space dimension 10, we can certify entanglement in a subspace of dimension 63 in less than 6 seconds on a standard computer. So here the maximum possible dimension would be 81, 9 squared, so we're not quite there. But this is just a one-sided algorithm, so let me show you the complete hierarchy, and this is based on Hilbert's Nullstellensatz. So this whole hierarchy is what someone in algebraic geometry would call a Nullstellensatz certificate for this problem. So the kth level of the hierarchy just kind of does what you would expect. Instead of looking at U tensor twice intersect X sep 2, you look at U tensor K times intersect X sep K times. And this is indeed a hierarchy. At each level, this linear system that you're solving is strictly stronger than the one before. And it's actually complete in that if you go up high enough in the number of levels, then the output fail ends up being equivalent to U containing a product vector. So it really solves the full decision problem in the limit, or at some actually fixed level. We can have analogous hierarchies for certifying other notions of entanglement. So I'm going to be very general here, and I'm going to fix some subset X of some Hilbert space CD. And I want you to think of this as being like CD has some underlying local structure, and X is some set representing a set of low entanglement. And you can kind of imagine that there are analogous applications of showing that a linear subspace avoids this set of low entanglement X, or X is now just some other set, maybe the Schmidt rank R vectors instead of Schmidt rank 1. So you can write down the same hierarchy for this general problem. It just asks if U tensor K has any intersection with XK. And this is again a complete hierarchy by Hilbert's Nullstellensatz. Okay. So we have kind of a general result, general works extremely well theorem for many sets X that you might care about. So we have a general result, which in particular implies these examples which we would be interested in. So the thing to note here is that at each level, so the first thing to look at is the upper right. For generic subspace U of dimension less than or equal to the alien, it holds that our algorithm certifies that notion of entanglement at k equal the spider level. So, for example, for Schmidt rank less than or equal to R states, if that's our notion of non-entangled, our algorithm already at the R plus first level can certify entanglement of a generic subspace of dimension, a constant multiple of the total Hilbert space dimension. Okay, and the same kind of property holds for for showing complete entanglement in the multi-party setting, or genuine entanglement in the multi-party setting, or some more exotic ones like showing that a subspace avoids the slice rank 1 states, or has large bond dimension as a matrix product state. In all of these cases, we have the same kind of takeaway, that our algorithm certifies entanglement of subspaces, generically chosen subspaces, of dimension a constant multiple of the maximum possible, the underlying Hilbert space dimension, in polynomial time. And the polynomial time comes from the fact that the level is always a constant that we have to go to. Okay, I'm going to move now to a robust version of the hierarchy. So instead of just trying to answer this decision problem, determining whether U avoids X or it intersects X, we're going to try to compute the maximum overlap between an element of X and an element of U. And this kind of is more succinctly represented as the maximum overlap between an element of X and the projection onto U. It's completely equivalent. And I'll denote this by Hx of U for historical reasons. This is indeed a robust generalization, because U avoids X if and only if the maximum overlap between an element of X and an element of U is less than 1. So we have the following sort of robust version of the hierarchy that I showed you on the previous in the previous slides. So what do? I'm jumping right to the general setting, where you have a general set X, and I haven't mentioned this yet, but the exact condition we need is that X is an algebraic variety, a conic algebraic variety. So what do? You take, you let mu k be the maximum eigenvalue of, you take the projection onto U, you tensor with identity k minus 1 times. So this is the kth level of the hierarchy. You're working in this k-fold space. And then you sandwich that by the projections onto this space xk, which we're coming to love in this talk. Then these mu k's form a non-increasing sequence that converges down to this maximum overlap. So at each level, you get an upper bound on the maximum overlap, and in the limit, they converge down to the true overlap. Okay. So this also holds, this theorem also holds for any Hermitian operator. So maybe you're not trying to take just the maximum overlap between an element of X and the projection onto a subspace, but you can actually take any Hermitian operator, and the same result will hold. That you get this hierarchy of maximum eigenvalue computations, which converges down to the maximum overlap between an element of X and a Hermitian operator. Okay. And the proof of this theorem is basically the DPS hierarchy, and some other little tricks, but that's kind of the underlying machinery. But we can actually use it to extend the DPS hierarchy to certifying other notions of separability. So just like it's natural to ask if a mixed state can be written as a convex combination of product states, it's also natural to ask if your mixed state can be written as a convex combination of some other states of low entanglement. So that's why we are coining this term, exorable. State rho is exorable if it can be written as a convex combination of pure states, each coming from this fixed set X, some set of low entanglement. So what we obtain as a corollary to this robust hierarchy is that a mixed state rho is exorable if and only if, for all k, there exists an extension, sigma, to k system, k copies of CD, such that the image of sigma is contained in this xk. So for example, we can recover the symmetric extensions hierarchy of DPS, which says that a state rho is separable if and only if for all k there exists an extension, sigma of rho, for which its image is contained in this symmetric space. Okay. So the proof of this corollary uses the robust hierarchy as well as the hyperplane separation theorem, this very basic result from convex analysis, which is the connection between exorability and this maximum overlap between a Hermitian operator and an element of X. Okay, so these kind of these W's in this thing form play the role of the entanglement witness when you're looking at the product states, and I'm calling them an inexorability witness for the more general setting. So let's look at our examples. We obtain hierarchies of for showing determining whether state is exorable in all these kind of natural settings. So in particular, we reproduce this hierarchy of Gund and Moroder and Tone from 2015. And of course, the multi-party version of the DPS hierarchy, as well as a hierarchy for biseparable states, and like showing that biseparable states. This means that you're showing that your state is biseparable. It can be written as a convex combination of states, pure states, each of which are biseparable. Slice rank 1 version is a little more exotic. Matrix product states of bond dimension less than or equal to R. This is checking if your state can be written as a convex combination of pure states, each of bond dimension less than or equal to R. The key takeaway here is we've extended the symmetric extensions hierarchy for separability to a different extensions hierarchy for exorability. So sort of instead of a symmetric constraint on your extensions, you have a different linear constraint on the extension depending on what your set X is. Okay. All right, so I'm going to wrap up. I showed you complete hierarchies of linear systems for certifying entanglement of a subspace. And these sort of work extremely well already at early levels in that they certify what the corresponding notion of entanglement in a linear generic subspace of dimension, a constant multiple of the entire Hilbert space dimension in polynomial time. And then I briefly mentioned sort of corresponding polynomial time algorithms for finding low entanglement elements of a subspace, which also work extremely well sort of in a similar sense. And these two results are sort of spread over these two papers you can find on the archive. And then I showed you a robust version of the first hierarchy, a hierarchy for certifying entanglement of a subspace, and use that to extend the symmetric extensions hierarchy of DPS to sort of analogous hierarchies for testing Schmidt number, biseparability, and exorability more generally. And that kind of part is coming soon to an archive near you. So thanks.
Okay, questions? There's one. Could we throw the cubic? Yes, I think there's two, right?
By imposing an additional condition for the set U, can we decreasing the necessary dimension for the efficient?
Yeah, I don't know. Like, for example, restricting to like fermionic space or something, or
yeah. For example, we consider only the local unitary symmetric U set U, for example.
Yeah, I would expect the same sort of. I would expect the same completeness result holds. You have to go up to say until it's exponential time. I mean, it'll be NP hard, kind of whatever you do. And I would expect sort of a similar result holds where you just go up to the first non-trivial level, and you get sort of constant multiple of the maximum possible, it can certify there.
Is there any additional strong condition for the decreasing the necessary
Sorry?
condition? How about more strong condition?
Extra condition?
So yes, more strong extra condition.
Probably.
Okay.
I don't know.
It's one.
I just wanted to ask, like, why does the algorithm get easier when you tensor like these spaces with themselves?
Why does it get easier?
Yeah, I mean, like,
I mean, intuitively, like the problem you're solving is becoming larger. Instead of looking at 2 copies of CD, you're looking at 4 copies of CD. In the more general case, I'm using capital D, and it's instead of 1 copy, it's 2 copies. But yeah, so I guess at the expense of solving a more difficult problem, you gain more in the end.
okay, thanks.
Yeah.
There's one there first, and then you will be the next. Yes.
Hello, thank you for the nice talk on entanglement testing. I was just wondering if you could elaborate on the Schmidt number separability testing.
Sure. So is the definition clear what I mean by...
Yeah, it is.
Okay. Yeah. Oh, yeah. So of course this linear constraint looks terrible, but it is just a linear constraint. But this is a good point to mention. Actually, computing this space xk, like writing down it's easy to say what it is abstractly, but writing down a basis for that space is non-trivial in general. For this case, we can write it down in general, but yeah, it can become complicated, and. In other cases, you can't write it, or it's an open problem to write down a base for that space. It ends up being sort of, in algebraic geometric terms, it ends up being equivalent to writing the generators for the ideal of the set in degree k. Yeah.
All right, thank you so much.
Thanks for sharing your impressive results. I didn't understand how you apply Hilbert's Nullstellensatz, so maybe you can say a few words about it. So the way I remember it is that if you have polynomials and the ideal they generate is not the full ring, you get a solution. How can you use this?
Yeah, so the Nullstellensatz, in this case, it says like you're trying to verify that the intersection of the subspace with your variety is just the 0 vector, right? And so one version of the Nullstellensatz says that if you have a set of polynomials, they cut out the empty set if and only if there's a polynomial combination of them that equals 1. There's an analogous result called the projective Nullstellensatz, which is certifying whether your variety is just the 0 vector.
Okay.
Okay. And similarly, it's a hierarchy of linear systems. In both cases, it's just a hierarchy of certifying linear. And the hierarchy is like the degree of the polynomials appearing in the polynomial combination. That's equaling 1 in the first case. So in both cases, you get a hierarchy of linear systems, and it turns out that what I've described to you is completely equivalent to the hierarchy of linear systems you would get if you wrote down the Nullstellensatz.
Okay, so Hilbert's Nullstellensatz in practice is this linear. Okay, I see. I didn't know that. Thanks.
Yeah.
We have one more.
Nice talk. Have you thought about, is it natural to think about the stabilizer rank in the same setting? Like if you're trying to have a witness for subspaces with certain stabilizer rank or something like this, or does that not work in the same way?
I guess, yeah, so there's only a finite number of stabilizer states. So it would be equivalent to checking if your subspace intersects some number of, I guess, some number of finite number of linear subspace. So
yeah, so it might not be complicated.
For linear subspaces, like you don't need the hierarchy, you just check it directly.
Yeah, that's right. Okay.
Yeah.
Okay. I think it's about time. So thanks Benjamin again.
Thanks.